Hello and welcome to everyone. So, in continuation with the last class, we will discuss today again the implementation of the theoretical framework which we have discussed in the last few classes on the volatility models. In the last implementation class, what we have discussed about how to compute the volatility. Then we also discussed about the ARCH effect. So, today we will be discussing about the GARCH and its different extensions. So again we are following the same steps, that is we have this our screen here. So that is the basically project base. Here you can see the name of the project, that is week 10 lecture number 50, and this is the basically our implementation of the theoretical models which we have discussed. So here we have the ARCH script by the name of GARCH. So we'll be opening this. So once we open that, here we have those ARCH codes and different sections of the ARCH. Now, if you recall, in the last lecture, we had here a symbol with the warning that certain packages are not installed in this particular machine system, and you have whether you want to install or not. Since we have installed in the previous lecture and we are using the same computer here, now we don't have that message because all those packages which we required in this is already installed. So if it is installed, then we do not have to run these particular commands here because already we have installed those packages. So but what we have to do, we have to attach those or call those packages into this particular session, and for that we will be using the function library. So here you can see we are using the function library here, and we are loading all those packages. So first, to load the package quant mode, we are using the function here, the library, and the package name here. So to run that, either we can use the button here, radio button, that is run, or we can use the shortcut keys, that is control plus enter in your keyboard. So if you are using control plus enter, so you can see here we have that particular package. So in the next line we can use, and the again next line. So if we keep continue, so all these packages we recall. So these are the basically what you getting, these are getting warning messages which says that this particular package was built under the R version 4.42. so that means the older version of R may not work. So once we have installed and call those packages which we required for this particular session, then what we have to do next is the downloading the data. So again we have I have not downloaded the data here in the Excel format. I am downloading the data which is required for this particular session. I am downloading directly from the internet. So we have to have the internet connection. So for that, again, like the previous class, I am using the function get symbol from the quant mode package, and then here we have to write the ticker name, and then we have to write the source. So I am using the Yahoo Finance, so it is from Yahoo Finance, and the date from where we need the data. So this is the data, daily data from 1st January 1996 to 1st November 2024. So let us download the data. So again we are using the control enter. So once we use that data, so here you can see that we have the data. That data has been stored into the SBI n.ns object name, and this is an XTS object, that is a time frame object we have. If you click on that, here we can see the different columns of that. So it is the open price, high price, low price, close, and volume, and adjusted. So these things already we have talked into the first week, what we mean by the different, this high, low, open, and close, and adjusted prices here. So here we will be using this close prices for our calculations. So let's take that. So now we are using that. So we are extracting that particular column and storing that into this particular data frame here. So W data is the name of the new data frame which we are creating, and this is the assignment operator, and here CL is the reference of that particular column, and this is the data name where they have to look for this clause. So if you are executing this here, so what we can see, we have created another data frame where this is the only that particular column is stored. So once stored, so we can rename the data, or later we will see when we take the log return, there we change. So like the previous lectures, here we are looking the first 6 rows or first 6 observations of that particular data. So for that we are using the command h head, then the data frame name into the parenthesis. So here you can observe those are the first 6 observations we have. Then what is the starting date? So if you wanted to find out that, so here if we run here, so you can see starting date is the 1st January 1996. We can also check for the end date, so that is 31st October 2024. So remember, here we have given 2 here, but however on the 1st November might be holiday, that is the data is not there, so we have getting the data only 31st October 2024. Then if you wanted to summarize the data, so we can use the function summary, which is the command from the base R. We don't have to install any packages to use this particular command here. So here we are getting the basic statistics. So this is the basically what we have, the time index. For time index minimum, obviously it will be 1st January 1996, and the maximum is 31st October 2024. So because these are the data, so this is the information about the data. And here basically our concern is the second variable, that is SBINS close. So the minimum is 13.35, first quartile is 29.02, and median is 177.96. Mean is on an average price is 195.71, and maximum is 905.65. NAs, that is the missing observations, we have 9. So we can use this particular command to find out the missing observations. So here we have missing observation, so it is again counting 9. So that means both we are getting the same. Now then once we have the missing observations, then we will not be able to use any time series model. So for that, what we have to do, first we have to remove those missing observations. So for that, what we use the command, we are using the command na.omit. That means wherever we have a na, we should remove those rows, and where they will look for the missing observations, this particular data frame. Then what we have to do, after removing that, again we are storing the same in the same data. So basically we are replacing. So we remove that, and again we restore or replace the old one with the new. So we run here. Now if you want to see is there any missing number, if you wanted to check, we can do that. Sum is dot na, then in the parenthesis w data frame name. If I running here, now you can see here that there is no missing, because already we have removed those missing observations. So that's now we have prepared the data. So once we prepare the data for the calculation, the next step is we have to visualize the data to examine the pattern. By looking at the graph, we can find out whether the data is stationary or it is non-stationary, how it, what is the pattern of data, where it is maximum, where it is minimum, how it evolves. So all those basic information we can get by looking at the graph. So for that, what we are using ggts display. So gg is the from the grammar of graphics, that is ggplot2, that commands belongs from that. Basically it is in the time series. So this ggts display is coming from the package of T series, that basically short form of the time series. Then in that particular command, what we have to do, we have to first write the data name. So here, because we have only single variable, that's why we are writing w data. If it would have been multiple variables or multiple columns, then we can specify the column by using the assessor symbol, that is the dollar symbol. However, we have the only one column, so by default it will take only that particular column. Then here we are looking the plot type, what is partial, or so this plot type is basically, we'll see when we have that particular image, there will be three columns in that particular chart. The first half we have one column, then the second half we have the two columns, then the right bottom side column we have the different options to draw that. We can use the histogram, or we can use the correlation, or we can use the partial. When we are using partial, that means basically we are asking to plot the partial ACF, that is the PACF. Then this smooth is equal to 2 is the function, that basically logical function. Basically it will draw a smooth curve on the data. Then here the theme classic, basically these are the optional argument we have. So if you don't put, there is not an issue. Theme, basically in the ggplot2 we have the how the outer side of the graph should look like. So let's execute this here. So when we are executing, we get this particular graph. So let us zoom it. So here you can see we have the PACF. So this particular graph, we can have the other options. For example, we can have the histogram here instead of PACF. We can have the correlation chart instead of the PACF. So those things, by changing this option, we can get. Then by smoothness, here you can see we have the blue line. So this blue line we get by using the here the logical function true. If you put the false, we will not have that particular graph here. So this is if we use here, so we can see now there is no more that blue smooth curve. So that's the option we have. Now this theme classic is basically here how the outer background of this particular graph looks like, that we can control using the different themes. Whether we have the theme classic, then the other themes also available there. For example, suppose we may have theme, for example we have theme dark, so we can use theme dark here. Then so let us say what we have. So this is the theme dark. So the what is the background of the graph, outer side of the graph looks like, that we can control. Then here if we look in the graph of the series, that from the graph it is clearly visible that data is non-stationary. However, to get it confirmed, what we are using the unit root test. So here we are using this unit root, that is the ADF unit root test we are doing. So here we have to write the data, then the type, we have the three types already we have discussed earlier, that here we are using, let us say, trained. Then how to select the legs. So here we are using, let us say, AIC or BIC. For example, here let us use BIC. So if we directly run, we get the direct result here. So it will be only one line result. So it's better to store it. Let us say we are storing it in the ADF. Now let us run here. So now no more result. So that result has been stored into ADF. So that you can see here we have. Now either directly we can write here. So we will get the same. We will not get the full result. So it's better if we use summary package, then we run this. So now we will get the whole detail here. So once we use the summary, then here we can see this we have from this whole, all the regression equations call. So every result will appear here. So now if you look here, what is the test statistic? We have test statistic minus 0.9783. What is the critical value we have? The critical value we have this. So to reject the null, where the null is the series is stationary. For that, what we have to do? That we have to compare this critical value with the calculated value, that is 0.9783 here. If it is more big negative than this, then we will reject the null. So here the null is the data is non-stationary. However, you can see this is not the more negative, it is the less negative. Or other way to examine that, in absolute value also this should be more than the absolute critical value here. That means without the sign, if you are comparing, even then it should be larger than this. Either we can say if you are comparing with the sign, then we should say that calculated value, the test statistics which we are getting, that should be more negative. If we are not taking care of the sign, we are comparing the absolute value, then the calculated value should be larger than the critical value. Then only we will be able to reject the null hypothesis. Rejecting the null hypothesis here means rejecting the null hypothesis means that the data is stationary, because the null is the data is non-stationary. Here we are not able to reject, that means the data is non-stationary. So here at the two step we have used that particular. So we executed the ADF, stored into the object ADF, then we use the function summary. However, that can be used directly here. That is, without storing, we can get the result printed in that particular form. For that we have used the summary. Then within that function we have used another function. So in the same task, here we have performed the two step. It could be performed into the single step by using this strategy, that is function within the function we have used. So now if we execute this, so here we can get the again the same result here as we have done here. Only thing here differs, we have instead of trend we are using only drift, and here we are using AIC instead of BIC. So these are the options we have. However, both these results shows that both these results show us that the data is non-stationary. So once the data is non-stationary, we cannot use GARCH. So what we are doing now, we have to make the stationary. How we make the stationary? Taking the difference. So here by taking difference means basically calculating the return. So the first thing what we are doing here, we are taking the difference log of W data. That means basically we are calculating the return here. So let us execute that. We are keeping the name RTCS because it is in the return form. So let's execute here. So once we are executing this, so here we can see we have the new data set, that is RTCS. So this, so it is not in the price form now, rather than it is in the return form. If you multiply with 100, it becomes in percentage. However, multiplying all the observations with 100 does not make any qualitative change into the results. So therefore, we often use this logarithmic form to calculate the return. So now again, in the next command here, what we are doing, we are removing the first observation, because the first observation is missing as we have taken the difference. So that we can observe here, this the first observation is now missing. Why the first observation is missing? Because while calculating the return, so while calculating the return, basically we have taken the difference. So delta yt is equal to yt minus 1, then the delta, the here it will be 1, now here it will be 2, so that will be here, this is, so basically, so to calculate the difference, what we have to do, for example, this yt, it is becomes y2 minus y1. So basically now we will consider it as 1. So here y3 is now y3 minus y2. So we lose here the first observation y1. So therefore we are removing here that particular observation. So minus 1 means delete the first observation, comma, here if you are leaving blank, that means all the columns. Since we have only one column, so there is no as such any difference. If we have the more than one column, we can ask, yes, delete the observation only of the first column, not the other column. So that we can control here. So if you are running it here, now if you look this RTS, so there is no more NA, that is the missing observation we have. So once we do, then the next again let us plot this here. So now if you see the plotting here, so what we can observe from that series seems quite pretty stationary. So obviously here we can change the color of that. So we can change color as, let us say, blue here. So if now we run, we get the graph is now blue. Then again, now again rechecking for the stationarity. So here the same thing we have doing. So let us run here. So we can see here the statistics is minus 59.629, and that is the more negative than this. So obviously the series is stationary now. So once it is stationary, then now we are going further task. So let us again visualize the data here. So we are visualizing the same data, just we have added the title of the graph, or we can use the same GGTS display where we will be having the ACF as well as the PACF. So here we can say these are the return graph, and here we have the ACF, and here we will have the PACF. So here ACF, we can say we have the multiple autocorrelation we have here, one we have here, this. So all these places we have this autocorrelation here, and here we have the PACF, the two PACF here we have. Now using this, we can have a hint what are the should be the lag of ARMA. So it seems that it is quite reasonable to have the AR and MA structure into our main equation here. So now to test the presence of the this arch effect, so we are using this arch effect here. So let us say this here. So this This is the ARCH test is the command to examine the presence of ARCH test, autoregressive conditional heteroscedasticity effect in a particular series. That series name here we have given, and the lax is equal to 1, d mean is true, so that is d meaning of the series here. So let us see the data here. So this is the result we have. So here we have the null hypothesis, the no arch effects. So that means if we wanted, if the data doesn't have arch effect, then we have to accept. If it have, then we will get the test statistic, which will push us to reject that. So here the p value is less than 2.2 e minus 16, that is, it is quite close to 0, because here this is the scientific representation we have. So 2 minus 1 e to the power minus 2. So this is basically what we have a scientific representation of the number here. So if we have, let us say, this twice minus e, so let us say if we have twice e minus 2, that means twice divided by 10 to the power minus 2, so that is 2 upon 100, so that is 0.02. If it would have been positive, minus plus 2, that means it is twice into 10 to the power 2. So that is known as the scientific representation of the large numbers. So here we can see the result, it is 2.2 e minus 16, that means it is quite close to 0. If p value is equal to 0, that means we should reject the null. If p value is closer to 1, we have to accept the null. So here we are rejecting the null. That null is that there is no arch effect. That means we conclude that there is the arch effect. Now, to check the presence of the GARCH effect, so what we are doing here, basically here we are taking the square root of the our series here. So if you are doing, let us say here, so this is nothing but the square return now we have calculated. So let us say we have the both data. So let's see bind here, that is RTCS and comma SRTCS. So let's have, we have the B data. Now we can see. So characteristics we have. So let us say RTCS. So here we can see this is the close and this is the close one. Basically this is the square of this particular series here. So that's we have squared that. So this is just so that these here in this SRTCS is nothing but the square of the RTCS, that is the return. Then we are plotting that particular square series here. So this is the plot of that squared returns. So this is the plot of the squared return. Now in that plot, so once we plot that, then how we can find out whether there is the presence of GARCH. So when we say GARCH, basically what we are looking at is their presence of volatility clustering. So if there will be volatility clustering, then this square returns will be show the burst of high and low value clustered into the different chunks. So if we carefully look here, we can see there is the chunk of this, there is the chunk of this. So you can see the certain chunks of the bursts here. Those are the chunks we have of the cluster square returns. If that is the case, we can guess there might be the presence of volatility clustering. If that is the case, then obviously the GARCH model is far better than the other time series model. Then let us find out the ACF of this squared returns. So that will also reflect the same information. So ACF, that is, we use the function ACF for the autocorrelation function. So here we can see the autocorrelation function of the square return. So obviously you can see there is the spikes outside of this confidence interval. So all those spikes which is outside of this blue lines, that is the confidence interval, that means they are the significant. So we can see there is the series of autocorrelations we have which is significant. So there is the problem of autocorrelation. If that is the case, then obviously there is the presence of volatility clustering. Then finally, we will use the statistical test to examine that. So that is the box Pierce test which we have discussed in the theoretical lectures. So here we are using that is the box dot test. You might remember that R is very case sensitive. Case sensitive means that the capital letter, a small letter differentiation R can read. So for that we have to be careful. For example, in the here the command box test, the B is the capital. So we have to write the capital. If you are writing the small, you will get the error. So box test, then what we have to do? We have to give the series name, then we have to give what is the lag order, then the which type of text we are using, Jung and box test. Suppose you wanted to know the further details of this, the best way to know that, we can click on the help. Then here we can type that, let us say box. So here we can see the function name box test. So once when we have this, then we can see here all the details. So what is the description, box Pierce or Jung box test statistics for examining the null hypothesis of independence in a given time series. And here we have usage, different the argument. So the test to be performed, partial matching is used. So here we have the details. So statistics, parameters, the p-value, method. So it method the type, what we can say. Here we have the examples also. So here we have the L-Jung box. We can use the L-Jung for the box Pierce type rather than Jung and box. So these are the information we can get from here. The p-value is small, reject the null hypothesis independence this. So let us calculate here. So again here the p-value is very close to 0. That means we have to reject the null hypothesis of no autocorrelation. That means there is the dependency, there is the autocorrelation. So all these informations reflects that there is the presence of the GARCH effect. So once we done that, then what we have to do, like the ARCH, we have to estimate, fit the model into our data. Then like the ARCH, the GARCH also have the two part. One where we have to give the specification, we have to supply what should be the mean equation, what should be the variance equation. Then in the second part we estimate. So when we are telling that what is the mean equation, you may recall from the previous theoretical framework, any GARCH model, how we represent. We represent the GARCH model here. Let us say this RT is equal to mu plus here epsilon t, where this epsilon t follows the normal distribution with mean 0 and variance condition HT, that is the conditional variance here. So this is what we call the mean equation, and here this HT follows, let's say omega plus alpha u epsilon t minus 1 square plus beta HT minus 1. So this is what we call the ARCH term, and this is what we call the GARCH term. So when we say in the R to specify the mean, we wanted to specify the structure of the mean. Here we wanted to specify the structure of the variance equation. So how many terms of ARCH, how many terms of GARCH? So those are the basically concerned. Here we can have, let us say, RT equal to mu plus let us say gamma 1 RT minus 1. So this will be the AR structure, plus let us say if we have theta epsilon t minus 1, so that is the MA structure we have. So for the first, what we do, we specify the GARCH structure of, that is the variance structure here. So for that, this is the GARCH spec, basically specification of GARCH we are creating, and we are storing that into the particular object here. Then to create the specification, we use the function uGARCH spec. Then after that, we are giving the structure of the variance equation here. So variance model is equal to list model SGARCH. So that is SGARCH is from the family, we are using that. Then the GARCH order is equal to C, that is that in combination of the two information we are giving 1 1. So first is for the ARCH term, second is for the GARCH term. Then comma, after that now we are modeling the mean model list ARMA order C 0 0 include mean true. So mean, so that when we are include dot mean is equal to true, that means we are including this particular constant term into the mean equation. However, we are not adding, so exact specification right now we are giving RT is equal to mu plus epsilon t. So that's the structure we are using for the mean equation. Then the others are there are the different options we have. For example, which kind of the distribution we are assuming, which kind of method for maximization we will use, all those we can specify here. So let us run that. So the GARCH specification you can see here, that has been stored here, the former class uGARCH specification. Now that specification we are using here uGARCH fit. Now this will fit that particular structure for the our data here. So uGARCH fit spec is equal to, again here what is the specification, this is the specification we have. Then out dot sample equal to 10, that means for the comparison of the forecast we are keeping 10 observations out of the sample. Then data, where is the what is the data source that we have to write. So once we execute this 2, so here the GARCH fit, it is fitting that particular observation here. Then we can see here the results has been stored and it has been updated. Now we wanted to print those results. So print, then that GARCH estimated model has been stored into this name. So here if we click, so here we have all the information here. Now let us look the information. So from here all the results is all about the GARCH model. Here lot of different tests, the parameter value, so those every things we have here. So let us see here conditional variance dynamic, here the SGARCH 1 1. Mean model, we don't have any AR term, MA term or F. Then distribution is the normal distribution. Now let us look at the parameters. So every p value reflects those parameters we have estimated is significant, except here if we are using the robust error, then here it is showing little 0.1. So every p value reflects that the estimated parameters are significant. Now these are the information criteria we have. For the comparison we will be using these information criteria. Then here box text on the standardized residuals. So whatever we have done residuals on that, what is the basically we have. Then we have same the weighted. So by looking here we it seems to be there is the problem of autocorrelation. Now the another test we have a weighted arch LM test, whether there is the arch effect or not. So by looking the p value we can accept there is no more arch effect on those estimated residuals. Now this Nablom stability test is basically about whether the parameters are stable. So if I'm changing the sample size, will it change here? So here we have the joint statistics and individual statistics for each equation, and we have the joint. So if we compare the joint, it seems there is the uh, here it 1%, and that is very slightly. Here we have 1.59, it is 1.6. So this says that our model parameters are stable. If it would not have been stable, then it would have been better to use the T-GARCH, that is the threshold GARCH, or the other extensions we could have tried here. This sign bias test is basically say whether we have leverage effect or not. Here the significance positive sign bias, so that means the positive change or positive fluctuation do have a impact on the volatility. So this the basically about the leverage effect we have. Then here adjusted Pearson of goodness of fit, those are the basically we have talked about here. Now once we have done, we can plot the GARCH diagnostics. So if we use the plot, then the GARCH model which we have estimated, for example here, then which is equal to all means all the information which is available, statistically available, we can plot it. So let us do that. So it is telling that the figure margins too large, that means it may not be possible to plot here. So now since we have increased the screen size here, this particular column, so now it is able to show that particular graph. So whenever you get the option error that is these figure margins are too large, so you can expand this particular column where basically you wanted to the graph to display. So now if we zoom out this particular graph, so here we have this particular graph. So this is the series with the two conditional variation superimposed. This is so conditional standard deviation, that is versus the return. So here is the one concern. This is the conditional variance which we have estimated, standard deviation, not the variance. And here we have this, the gray lines are the returns. So from this clearly we can observe that there the higher the fluctuations, the higher the volatility we have. And this is the ACF of the observation, that is for the series, and ACF of the squared observation, ACF of the absolute observations, and the cross correlation squared versus actual observations we have. And here we have the empirical density of standardized residual. So it is, we can see here that is quite close to the normal distribution we have. This QQ plot, so here we can see at the end there is the divergence. So one divergence is here, another is here, so it shows there is the autocorrelation will be there. So it is the ACF of the standardized residual. So you can see here this there the some versions of autocorrelation we do have. So let us check that using the statistics here. So by looking this graph, we can see here there is the minor. So this one is obviously it will be 1 because variance divided by variance here. So these are the a very minor significance we have the ACF. Now similarly we will use the box test again. So here we can see now the p value is 0.25, so we can accept the null, there is no auto correlation. Now the information criteria of this particular model I am storing in G11. So basically to make the comparison. Similarly, we are estimating the GARCH 1, 2, that is the first ARCH term, then the 2 GARCH term, that is beta 1 st minus 1 and beta 2 st minus 2. So let us estimate these models here. Now only thing you have to keep in mind here, when making the specification, what we have done, we have given the specification of the variance model only, not the mean model. So mean model, if you are not writing anything, that means it will take the default values. So let us say what are the default values we have for the mean model. So that we can see at the parameters. So here if you see AR1 and MA1, that is the lags of UT and epsilon t, and the RT has been taken into the mean equation. However, if you see the p value, this 2 is not significant. Then like the previous all of the informations here we have. So similarly we are GARCH 2, then we have GARCH 1, 2, then here we are. So now we are storing a GARCH 1, 2, an alternative model where we are also providing the mean model, where we are listing that there should not be AR and MA term. So if you are estimating this, so we can see the information here. Now if we compare the parameters, we do not have AR and MA model in this because we have specified the mean equation and we have not included the AR and MA term. So by default, they assume AR term 1 and MA term 1 into the mean of the equation. Now since we have seen there is the certain issue, for that what we are choosing, now we are using the alternative, that is the GARCH M model we are specifying. So the variance equation we have GARCH order C11 and the mean model we have this. Then we are including ARCH 1 model here and ARCH PO2 here. So basically we are including a mean equation here. In the mean we are including this ARCH term and the GARCH term. So the GARCH M model. So we are estimating this and having this. So if we see that result in the parameters, so in the parameter we can see here alpha 1 and beta 1. So these are significant. So that means GARCH M may capture the better information. Similarly, we can have the threshold GARCH because there was the instability in the model. So here we are including the variance model, F GARCH, sub model, T GARCH, then we are using this. So we are having here GARCH model. So here we have beta 1 and eta 1. So this is the basically this T GARCH term here. So again it is significant we have. Similarly, we have the EGARCH, the model EGARCH and the GARCH order C11. So here we can estimate, and this the results we can observe here. Then this is the, here we have gamma 1, which is the basically for EGARCH term. Again it is also significant. So all those we have estimated. However, we can see in the GARCH M model is also parameters are significant. GARCH T GARCH is also significant. E GARCH is also significant. In these competing models, which model we should choose? So one way out is that we can compare the information criteria, and those models which have the minimum information criteria, that we can choose as the final model. So to make the comparison, here we are storing all the information criteria here from all the models. Then we are collecting that here in the data frame and we are printing. So now here we can compare all those models information criteria. If you are believing in AIC, so it's what it says, minus 4.801, that is the GARCH 1, 2 has the minimum AIC. So that means according to ARC, this is the best model we have. And if you are using the BIC, then this particular model, that is GARCH 12A, that it seems better. If you are using the HQIC, then again the GARCH 12 is better. So assuming that this GARCH 12 is better, here we are using those. So we can plot this AIC information also. But however, in graph it is quite difficult to see that minor differences here. So we can then use the GARCH to forecast the volatility model. So we can plot. So here this is the forecasted value we have of this GARCH model. However, what we have doing here, we are using the GARCH 1-2 model as the best final model. So we are using the finally estimating the GARCH 1-2 model. So there is the one term of ARCH and the two term of GARCH into the variance. There is no term of AR and MA in the mean equation, and we are not including T or E component or M component. So based on the information criteria, so here we are estimating that model, and this is the result we will get. So as we have the detail we can have, and now we are going the diagnostic for this. So here we are diagnostic test of this. Then the AC autocorrelation function we are doing. So there is very marginal autocorrelation we have. Now there is no more autocorrelation. Then we can have this GARCH effect. So obviously we can see here there is the 69. So there is no ARCH effect. Then we are using that particular model for the making the 10 horizon forecast. Then we are using this mean square error, mean absolute error, and DSC to measure the performance, forecasting performance. So in all these statistics, lower the number, the better the forecast. So we can see it is very close to here 0. So that means it is forecast seems quite good here. Now we are plotting those forecasting volatility here, and here we have this forecast. These are the actual, and here we have the forecast series. So that's how we can decide among the competing models, and we can compare the forecasted value here. So that's today we have discussed how we can implement the GARCH into the real world data. So today we took the data of SBI, State Bank of India, from 1996 to till 2024 daily data. Then we have tried to analyze that data using the GARCH and its different extensions. Hope it will be a learning experience and enriching experience for all of you. Thank you so much.